Okay, if you were with me for the constant velocity video, I'm going to follow the same kind of format now with a constant acceleration. So first, again, the reminder that this is a vector, which means that it does have direction, right? So includes direction. I am probably as guilty as many other physics teachers to often not to be formally and say which direction things are accelerating. So sometimes it'll just be obvious from the context, but officially you should always say the direction when you're talking about acceleration. The typical units are going to be meters per second squared, but every once in a while you'll find other odd ones, like you might get kilometers per hour squared and things like that. But there are the default, the base metric units is meters and seconds, so it'd be meters per second squared. I think we're just going to do one example here, and it's going to be, we'll do a basic example of a car. Maybe it's accelerating at positive 2 meters per second squared. In this case, by positive 2, I'm going to mean to the right. So one way to show it could be with oil drops. So if it starts at rest, I'll put even here, the starts at rest, so this would be a physics notation way of saying that. And then to begin with, it doesn't move very far, and then later on it moves farther. So you can see that unlike the constant velocity here, the dots are getting more spread out. And I'll even make this one start at the origin and then move away. So the oil drop doesn't tell you how much time is going between two drops, but it does tell you that you can always assume that they mean to be equal amounts of time, so it's speeding up. Well, let's see here. If I was to make a table, I'm going to be eventually making 3 tables. I'll be making a position time graph. I will also be making a velocity time graph and an acceleration time graph. You know what, let's do an acceleration time graph first. So the units here for acceleration, like I said, will be meters per second squared, and this will be seconds. This will be meters per second. This will be seconds. This is meters in seconds. So you see the transition here. So the big picture is how position is changing, that's what velocity is. How velocity is changing, that's what acceleration is. I said right in the outset that this is an example where the object is accelerating at positive 2 meters per second the whole time. So this is a pretty easy table of values to make out. So I'm going to say it's going 2 every time. The other thing that I mentioned over here is that we're going to be starting at 0 meters per second. That means the initial velocity is 0. So acceleration is the rate of change of velocity. In other words, if I go from 0 to 1 second, that means my delta t is equal to 1 second. Then my acceleration is equal to the rate at which velocity changes with respect to time. Here's our basic definition of velocity. So if delta t is 1, and the entire thing has to be 2, in this case 2 is going to be equal to something over 1, if that makes sense. My acceleration is 2. If 1 second goes by, the velocity better be changing by 2. So in other words, this is going to be going up by 2 every time. Here you can see the velocity is going up by steps of 2 every time. So it's a little bit harder to figure out the time. We're going to leave this at a blank for the next little while. I'll go over here and take a look at our graphs, and you're going to see very shortly as we do some examples over the next few days that the most helpful graph to do is the velocity time graph. So I'm going to try to be a little bit on the neat side here so I can make a useful graph. Here's a velocity versus time graph. I'm going to go and say, okay, so if I can take this table of values here, this one here, and then make a graph out of it. So my time has to go 0, 1, 2, and 3. And then my velocity, I know was going, I'll just go 2, 4, 6. I'll just go jump by 2, so it's easy to do. Now if I do those points after 1 second, at 0 it was 0, at 1 second it was at going 2 meters per second, after 2 seconds it was 4, and after 3 it was going 6. So here would be my graph. And in fact, if it's keeping on moving, I can even put an arrow at the end there. Alright, now let's consider how we're going to fill in these values for position time. So I guess the first one's easy. At time equals 0, the position is 0, but 1 second later, how far has it gone? Well, if you were just to look at this value 2 and say, well, it's going 2 meters per second, so it must have gone 2. It's like, well, at the end of that period of time, it was going 2 meters per second. At the beginning, it was only going 0 meters per second. It's speeding up. We can't use our v equals delta d over delta t and have it rearranged for this. This does not work right now. These ones don't work because it's not at a constant velocity. The velocity during the first second starts at 0 and ends at 2. So how are we going to figure out how far it goes after 1 second or 2 seconds or 3 seconds and all that? How are we going to figure all this out? So let's go back over here and remind ourselves that one of the things about our VT graph, and this is a big one, is that the area underneath, so this area in here, maybe I'll go back to red, this area in here tells us the displacement. Okay, so this is one of our big ideas here. So I'm going to just write this over here for one of our summaries here. The delta D is equal to the area and it's between the VT line and the x-axis. That's this space in here. So if we want to know how far it's gone in 1 second, we just want to get this area here. So I'm going to call this one area number 1. So I'm going to say delta D number 1 is going to be equal to this area there. And how do you figure out that area? Well, it's a triangle, so that would be the base times height divided by 2. The base is, well, this part here, that's 1 second, times the height, which is 2 meters per second. So 1 times 2 divided by 2, because it's a triangle, so that works out to 1 meter. So in other words, after 1 second, it has gone 1 meter. So I can put my value here instead of my question mark. I can say it's gone 1. How about after 2 seconds? So now I'll do a new triangle, and our new triangle is this one, this larger one over here, and I can say, well, delta D2 is equal to this second area, and again it's base times height divided by 2. In this case, the base will be 2, the height will be 4 divided by 2, so these 2's cancel out and I get 4 meters. Our last one, delta D3, will be a base of 3, a height of 6, and so we get 9 meters. So here we can put these numbers in. We get a 4 and then a 9. So interesting, I chose a 2 and we get a nice pattern here. You can see there's a square feature going on here. So to do our summary about these graphs here, there's a lot of information here. If you've got, this was our VT graph because I have in this case it was a constant 2 meters per second. If you have the velocity time graph and if you look at the area under the line, that will give you your position. So our position time graph, we took that table and we made some values out of it, it would look like this. It would give a DT graph that looks kind of like that shape there. In fact, here we'll sketch one real quick. Here we'll say this DT graph, because of that 0149 feature, kind of looks like this. So the important piece that we have just used is this part here. Oops, I'm supposed to highlight this area here under the VT graph. So it's this area over here. That can be used to find out the position values. So that's how to solve things graphically. This says formula, so that this is like a graphical way of thinking. The other formula that we have it's really a set of them, is we have the big 5. The big 5 kinematic ones that I won't write out because there's quite a few of them, there's 5 of them, and our sort of definition of acceleration. So When we've got constant velocity, we only use v equals delta d over delta t. That was the previous worksheet graphical organizer. When we have constant acceleration, we can use things, formulas. We can use the big 5 and the a is equal to delta v over delta t, or we can solve things graphically. And so there are two things we can look at. We can say that the displacement is the area between the VT line and the x-axis, and also acceleration is going to be equal to the slope of the VT graph. So the VT graph is very important, because if we look at the slope of that, that gives us our acceleration. If we look at the area under the line, that gives us our displacement. So maybe I'll just do that here. We'll make a VT graph. And in this case, I'll make it look like we had one here. Not every VT graph looks like it, obviously. So my A is equal to the slope, and my displacement is equal to the area. And I'll even maybe color in that area one more time here. Try to color that in. All right, and that is your summary.